All right. Thanks for joining me today. Today we're going to be talking about trapezoids and kites. So just as we've seen throughout the entire chapter here, as we've talked about different types of quadrilaterals, it's important to start with our definition, and then from there we'll build some properties. So today we're going to talk about a trapezoid. What's the definition? We're going to talk about a special type of trapezoid called an isosceles trapezoid. We'll talk about a special type of segment called a mid-segment in a trapezoid. We'll talk about kites. I think you guys will find today to be pretty straightforward. So let's get started. Okay, definition of a trapezoid. Okay, well, let's draw one first. If I'm going to draw a trapezoid, I'll probably draw something like this. Okay, like this. And then I'll come over here about like that. Okay. So I just did my best there to try to draw a trapezoid. What makes it a trapezoid? Okay, the fact that this side right here is parallel to that side. Okay? So when we take a look, okay, we've got a pair of opposite sides that are parallel. Now, how many pairs? Okay, exactly one. And that's how we define a trapezoid to be different than a parallelogram. Okay, we define a parallelogram to have two pairs of parallel sides, where the trapezoid has exactly one. It does not have two. So we're going to define a trapezoid first off to be a quadrilateral. Okay. Now that's different from rectangle, rhombus, square. We started by saying it's a parallelogram with different features. A trapezoid, like I just stated, it's not a parallelogram. So we start by saying it's a quadrilateral with exactly one pair of parallel sides. Now, a few other things to know here when we talk about a trapezoid, some terms that we're going to refer to. Each pair of parallel sides is considered a base. So this would be a base, and same with that. Okay. So there's two bases. The bases, are they the same length? No, they're not. Okay. If they were the same length, it would make it be a parallelogram. So we've got two different bases there. These two sides, okay, we call those the legs. This is a leg, and that's a leg. So our definition of a trapezoid, it's a quadrilateral, okay, with exactly one pair of parallel sides. It would look like that. Now, oftentimes, when we talk about trapezoids, students tend to think about an isosceles trapezoid. That's what they picture in their mind. Isosceles, we know from triangles, would be at least two congruent sides. So take a look at this trapezoid up here, and what would it mean to be an isosceles trapezoid? What would that look like? Well, one way that I like to think about an isosceles trapezoid is that I have an isosceles triangle, okay, so that these were congruent, okay, but then I take that and I slice off the top, okay, parallel to the bottom. Okay. Now, in the isosceles triangle, we know those full legs, those full lengths were congruent. In the isosceles trapezoid, we know that these are congruent. So you can see it looks like an isosceles trapezoid, looks like an isosceles triangle, but the top is just sliced off. You could say it's a truncated isosceles triangle. So this leg is congruent to that leg. So an isosceles trapezoid is a trapezoid, okay, in which the legs are congruent. Okay. Pretty simple. This is still a base, that's a base, but now when these are congruent, we call that an isosceles trapezoid. One other thing that we'll see with a trapezoid is one segment that's called a mid-segment. Okay. Does not have to be an isosceles trapezoid. So let me just draw just a normal trapezoid, not an isosceles trapezoid. Okay. A mid-segment. Okay. I think the word mid-segment does a good job describing it. It's a segment that connects the midpoint of one leg to the midpoint of the other. Okay. So this segment that I'm drawing in blue is the mid-segment. Let me get my parallel signs in there for the bases. All right, there it is. Okay, mid-segment of trapezoid connects the midpoint of one leg to the midpoint of the other. A segment connecting the midpoint of the legs of a trapezoid. There we go. All right, let's come back to the definition of a kite until we're ready to talk more about kites. Let's just look at trapezoids for now. Okay, can we show that quadrilateral CDEF is a trapezoid? Right? Well, what do we need to show? Okay, let's look back at the definition. We need to show it has exactly one pair of parallel sides. So this trapezoid is graphed on a coordinate plane. Okay, I want to show that I have exactly one pair of parallel sides. Now, looking at it, I think it's pretty clear that this side up here appears to be parallel to that side right there. Okay. How do I go about showing that? Okay. Well, when we graph it on a coordinate plane, it's easy to get some different formulas, things that we know about graphing involved. Okay. And I want to think about here for a second, what do I know about parallel lines? Okay. Well, I know that slopes of parallel lines are equal. Okay. So if I'm going to show that this is a trapezoid and I want to show that DE is parallel to CF, I can show that they have the same slope. So when we take a look, I'm going to put M for slope of DE equals, now you could use your slope formula, y2 minus y1 over x2 minus x1. Pretty easy to count here on the graph, rise over run. From D to E, we're what? Up 1 over 3. That has a slope of 1/3. Okay, how about the slope of CF? Well, just using rise over run, I can see that we are up 2 and over 1, 2, 3, 4, 5, 6. Okay. 6 over 2, that's 1/3. So take a look, DE and CF have the same slope, that means they're parallel. DE is parallel to CF. Okay. So is that enough to know for certain that CDEF is a trapezoid? Okay. Let's look back at the definition one more time. A quadrilateral with exactly one pair of parallel sides. Have we shown that there is exactly one pair of parallel sides? No, we've shown that there is one pair of parallel sides, but we haven't shown that there's exactly one. The second step to this is to show that CD is not parallel to EF. Okay. So let's take a look at those slopes. Slope of CD, rise over run, that's up 3 over 1. That's 3. Slope of EF. Down 2 over 2, that's negative 2 over 2. Slope of negative 1. Are those slopes the same? No, they're not. So we're going to say CD is not parallel to EF. Okay. Now we've shown we've got one pair of parallel sides. We have a pair that's not parallel. We've got exactly one. We can conclude CDEF is a trapezoid. Good. All right, where are we going to go from here? Okay, let's talk about our isosceles trapezoids here a little bit more. This theorem is going to sound pretty familiar to us. Each pair of base angles of an isosceles trapezoid are congruent. Okay? And hey, we've already mentioned that isosceles trapezoids remind us of an isosceles triangle. Okay? And what do we know in an isosceles triangle? Okay? We know that the base angles are congruent. That's the base angles theorem. what this theorem tells us is if it's an isosceles trapezoid, okay, we have two pairs of base angles, okay, and they have to be congruent. Okay, so we start with the isosceles trapezoid. We know that this pair of angles down there are congruent, and this pair of angles up there have to be congruent. Okay, now how are we going to go about showing this? So this proof is going to be a little bit different than anything we've done before. So let me start off with what the theorem says. Each pair of base angles of an isosceles trapezoid are congruent. So I'm starting just an isosceles trapezoid. So I'm starting with my pair of parallel bases, and I'm starting with this being congruent to that. So how do I prove that these pair of angles are congruent? How would I prove that those pair of angles are congruent? Well, I mean, we've already mentioned it several times. It reminds me of an isosceles triangle, and we definitely want to get an isosceles triangle involved here. But how do we do this? Okay. Well, one thing that we can do in geometry when we're trying to prove things is we can add into our drawing something that we define that would be useful. So what would be useful here is if I could get an isosceles triangle involved. But instead of extending it up like this, what I'm going to do is I'm going to simply add in a line, okay, like that. Now whenever we're adding in a line, we call it an auxiliary line. So I've added in this red auxiliary line. But I'm not just adding it just wherever. Okay, I want to define it to be something particular here that would be useful for me. Okay? And the way that I'm going to say is I'm going to draw this line so that it is parallel with this side over here. Okay? Now, why would I want to do that? How is that helpful for me? Take a minute here. If you want to pause the video and just think through how is just adding that one line going to help me show that this angle is congruent to that one. So take a second here. I'm going to pause my video. You pause yours and think. All right, so the big thing that we got to catch on is when I draw this parallel line, what type of quadrilateral did I make right here? I made a parallelogram, didn't I? Now, what is true about parallelograms? Okay. Well, there's a whole bunch of things that we know are true about parallelograms. That's why we spent a couple days looking at them. One of the things that we know is true in parallelogram is that opposite sides are congruent. So that tells me this side right here is congruent to the opposite side over here. Okay. Let me mark those congruent. Now, this has one mark. This is going to have one mark. Okay. Well, these are congruent. Those were congruent. What is true about these now? They're congruent. That would be the transitive property. And what did I just make right here? Not just any triangle. I just made an isosceles triangle. So, what do I know here in this isosceles triangle? Base angles are congruent. Jackpot. This angle is congruent to that one. Are we done then? Is that what we wanted to show? No, I want to show that this angle is congruent to that one. Okay, I want you to pause your video again and now think, how does the fact that these two angles are congruent help us show that this angle is congruent to that one? I'm going to pause my video. All right, what I hope you realized is that when we have parallel lines, we know a lot about angles. Consider these my parallel lines, this bottom base of the trapezoid as my transversal. We've got a pair of corresponding angles, right? This angle right here corresponds with that one. They're congruent. So if these two angles are congruent, those two angles have to be congruent as well. We've got the transitive property instead. Okay. So, working through, drawing this auxiliary line so that it's parallel to the other leg of the isosceles trapezoid gives us an isosceles triangle. Base angles are congruent. Okay, using corresponding angles, we're there. We use the transitive property a couple times, and we've got it. Okay. So, what should we write down here? I'm not going to say that we need to do the full two-column proof or a full paragraph proof, but let's just describe a little bit of our process of proving it. Okay. Draw an auxiliary line parallel to one of the legs. Okay. This creates, ooh, that was bad. Sorry for the poor handwriting. Okay. This creates an isosceles triangle with congruent base angles. Okay. Using corresponding angles with parallel lines gives us the base angles of the isosceles trapezoid as congruent. There we go. Pretty clever, isn't it? Okay, fun to come up with different ways to prove things. Now notice, okay, we only proved one part of theorem 8.14. We proved that these two angles are congruent. How do you suppose we could go about proving those top two angles are congruent? Would you have to approach it a little bit differently? Make some changes? Could you do something similar? Something that I'm going to let you guys think about. Alright, there's an isosceles triangle. Okay, here we go. Theorem 8.15. If one pair of base angles in a trapezoid are congruent, then the trapezoid is isosceles. So as long as we have a trapezoid where we only need one pair of base angles congruent, then the triangle is isosceles, or the trapezoid is isosceles. Okay, notice that's a little bit different. It's not quite the converse of that, but it's close. Okay, this one stated if the trapezoid is isosceles, both pairs of base angles are congruent. This one says you only need one pair of base angles congruent in a trapezoid to have an isosceles trapezoid. Okay, I'll leave that one to you guys on the proof there. Okay, let's apply it here to find some angle measures in a trapezoid. Find the missing angle measures. Let's find every angle measure we've got here. Notice it's a trapezoid. Okay, this tells me it's an isosceles trapezoid. I know the base angles are congruent. This angle right here needs to be congruent to that one. The measure of angle N, 50 degrees. Okay. How about angle L or angle M? Well, go back to the parallel bases. Treat this as a transversal. These two angles are consecutive interior angles, which we know are supplementary. Okay. Angle L has to be 130, and same with angle M. There we go. Okay. All right, I mentioned this the other day. I love these always, sometimes, or never questions here, so we're going to go through some dealing with trapezoids and isosceles trapezoid. Answer as always, sometimes, or never true. Okay, what I'd like you to do as you watch this, pause the video, answer these yourself, then play the video and see if you agreed with me. Okay, so go ahead, pause. All right, so here are my thoughts. A trapezoid is a parallelogram. Is that always, sometimes, or never true? The correct answer to that would be never. Okay. Trapezoid has exactly one pair of parallel sides. A parallelogram has two pair of parallel sides. We talked about that at the beginning in the definition of a trapezoid. Trapezoid is never a parallelogram. The bases of a trapezoid are parallel. Always, sometimes, or never true? The answer to that would be always. Okay, straight from the definition. Letter C, the base angles of an isosceles trapezoid are congruent. The base angles of an isosceles trapezoid are congruent. That is always true. That's just straight from our theorem right here, theorem 8.14. And letter D, the legs of a trapezoid are congruent. The answer to that? Sometimes. They are congruent if it's an isosceles trapezoid, but is every trapezoid an isosceles trapezoid? No, it's not, only some of the times. Okay, that's why our answer for this one is sometimes. All right. Okay, midsegment. Okay. Midsegment theorem for trapezoids. I want to jump into GeoGebra here, and I want to explore this midsegment concept. So I'm going to start off by making a trapezoid. I'm going to have to use parallel lines to do that. I'm going to use, let's see here, let's just go to our polygon tool. Okay. So I used one pair of parallel sides to make a trapezoid. Is this a trapezoid? Yes, it is. How about that? Yep. Okay. How about there? So I've got it so it's a trapezoid. Notice I'm going to try to avoid a parallelogram when these legs would be parallel as well. So let's take a look at a midsegment. As we define the midsegment, okay, we're going to go from midpoint to midpoint. So let me use my midpoint tool. Find the midpoint of this leg and the midpoint of that leg. I'm going to connect them with this segment that we call the midsegment. Okay. Now take a look here, and I want to see if you guys notice anything is true. Okay, let me just grab this and move it around. One of the things that we can see is true about the midsegment of a trapezoid is that it is always what compared to the bases of the trapezoid? It's always parallel, isn't it? So that's item number one. Item number two has to deal with their lengths. Okay. Now, they're already over here a little bit, but I'm going to put the lengths into our trapezoid. Oops, did not want that. And the length of the midsegment. There we go. So take a look at the lengths of the bases and take a look at the length of the midsegment. Do you notice anything to be true? Okay. Take a look at that example. Do you notice anything about the length of the midsegment compared to the length of the bases? Obviously, it's between those two numbers, but there's something a little bit more going on here. I'm trying to give you several examples to look at. All right. Okay, take a look at this. How does 9 compare to 4 and 14? One thing that students often notice first is that 9 is 5 units more than 4. It's 5 units less than 14. In other words, that makes this the average or the mean of the length of the bases. Okay, we can see that if I take 4 plus 14 divided by 2, gives me 9. Okay, so what we've just picked up here is our midsegment theorem for trapezoids. The midsegment of a trapezoid is parallel to each base, and its length is 1/2 the sum of the bases. So MN, notice midpoint, midpoint. It's parallel to both bases. MN is parallel to AB, and MN is parallel to CD. Okay. As for its length, it's 1/2 the sum of the lengths of the bases. It's the average, in other words. Okay, MN is 1/2 of AB plus CD. So if we take a look at this example, if I want to find MN, notice it is a midsegment. We've got midpoint and midpoint. mn, pretty easy. I'm going to take the average, 1/2 of the 16 plus the 9, the 1/2 the sum of the bases. Gives me mn is what? Half of 25. Mn is 12.5. All right, kites. Should we talk about kites? Okay, let's get back to the definition. We need to define it.